In this video, we want to talk about independence, or independent events as they're called in probability, and the multiplication rule. We've got some very interesting examples in this lecture, and unlike the previous lecture, it's not going to be all coin flip, die roll type stuff, so we're going to get into some more interesting concepts. So this lecture has three objectives. First thing we want to do is we want to identify what independent events are. Then we want to use the multiplication rule for independent events. In a follow-up lecture after this one, we'll talk in detail what dependent events are, and then the multiplication rule for dependent events. It's a different concept. And then we're going to end this lecture talking about how you compute at what's called at least probabilities. Okay, so the first thing, what exactly are independent events? So two different events here, E and F. Okay, so let's just say event E is like flipping a coin and getting heads. And event F is rolling a die and getting a 4. And let's just say actually getting a 6. Are independent if the occurrence of the event E in a probability experiment does not affect the probability of event F. So think about it. Does flipping a head have any impact on if you're going to roll a die and get a 6? No, it doesn't. So as long as what happened first does not change or the probability or affect the occurrence of the second event F, the events are independent. So the opposite is if two events are dependent, if the occurrence of event E in a probability experiment affects the probability of event F. So let me give you some more examples of these. Let me ask you if you think these are independent or dependent, and then I'll explain what I mean by affects the probability of another event. Okay, so suppose you draw a card from a standard deck of cards and then roll a die. The events of you draw a heart and roll an even number are independent, right? Because the result of choosing a card has no impact on a die roll. Okay, so those would be things that are independent. Generally, things that involve coin flips and die rolls are always independent. Okay, so suppose two 40-year-old women who live in the United States are randomly selected from all the women in the United States. The event woman 1 survives the year and woman 2 survives the year are independent, right? Because like if you select a woman in Connecticut and then you select another woman in Colorado, let's say, if they survive the year, it has no impact on each other. But here, suppose two women live in the same apartment complex. Two 40-year-old women live in the same apartment complex. Here, because you're selecting from a small sample size, just a small population size, just an apartment complex, the events woman 1 survives the year and woman 2 survives the year are dependent. Okay, let me give you another example of a dependent events. So you have event E. You draw a card from a deck without replacement. So after you draw it, you don't get it, you don't put it back, and you get a queen. And event F is you draw a second card after the first, and you get a queen. Well, if you think about it, what's the probability you draw a queen from the first deck of cards? Well, there's 4 queens, 52 cards, right? So if you draw a queen the first time, okay, now you go to draw another card, there's only 51 cards in the deck, and now how many queens are there? Only 3. So what happened first, drawing a queen, does change the occurrence that you're going to draw another queen. So there's another example of dependent events. Okay, so what we want to do now is we want to talk about what the multiplication rule for independent events are. And it's very, very simple. So the multiplication rule for independent events, if two events E and F are independent, then if you have the following. If I ask you, hey, what's the probability that event E and event F happens? Okay, or event E and event F occur. You just take the probability of the first event E and you multiply it by the probability of the second event F. That's it. That's all you have to do is just multiply the two probabilities. All right, so this one comes from a previous lecture. Okay, so suppose you flip a coin and then roll a die and you record your results. So remember, okay, we did the sample space for this from a previous lecture. And there were 12 things in the sample space. And I asked you actually this in a previous lecture, what's the probability you flip heads and you roll a 6? Well, just looking here, the probability that you do both flip heads and roll a 6, it should be 1/12 because there's only one way you can do it and there's 12 total outcomes. All right, but now let me show you how to use the formula that we just had. I see the AND statement here, the AND statement. So look, probability of E and F. Well, whenever I see the AND statement, that's going to tell me to multiply. So I'm going to take the probability of the first event, probability of flip heads, and you're going to multiply it by the probability of roll a 6 on a die. Well, since they're independent events, right? Flipping a coin and rolling a die are independent events, you just multiply. So the probability of flip heads is 1 out of 2. Probability of roll a 6 is 1 out of 6, right? So to multiply fractions, just multiply across. So 1 times 1 is 1. And 2 times 6 is 12. Look, you get the same thing. So this formula works. Let's try another one, okay? So the probability that a randomly selected female aged 60 years old will survive the year is 99.186, all right? And this is according to the National Vital Statistics Report. So what is the probability that 2 randomly selected 60-year-old females will survive the year? Well, look, the probability that they survive is 0.99186, okay? So if I'm going to select 2 at random, okay? So first off, we see the survival of the first female is independent of the survival of the second, okay? Like if we're just selecting at random, first female survives the year is going to have no impact on if the second female survives the year. So we have this, the probability they survive I have written up here. So look, it's just the probability the first survives and, this is important, and if I want them both to survive, the first needs to survive and the second needs to survive. So I see the and, so that's going to tell me right here to multiply. So it's the probability the first survives multiplied by the probability the second survives. Well, I know the probability they survive. It's 0.99186. So it's just 0.99186 times 0.99186, and you just get that, which is 0.9838. Piece of cake. We got it. Let's try this one. A manufacturer of exercise equipment knows that 10% of the products are defective. So look, we know the probability that a product is defective is 0.10. They also know that only 30% of their customers will actually use the equipment in the first year. So use equipment, which is a sad statistic if it's true. Will actually use equipment in the first year. So if there is a 1-year warranty on the equipment, what proportion of customers will actually make a valid warranty claim? Okay, well, so what needs to happen for them to make a valid warranty claim? So what happens is they need to be effective, it needs to be defective, and they need to use the equipment in the first year. So we're going to assume that defectiveness and the equipment are independent, right? Like I don't think it being defective would matter if someone tries to use it or not. No, they'll use it and then they'll say, hey, it's defective. So the probability that someone makes a valid claim would be it's defective and used. So we just said they're independent. So we see the and statement. That tells me to multiply. So the probability that it's defective, we know up here I said is 0.10. Probability they use the equipment is 0.3. So even though 10% of the equipment is defective, okay, the probability that there'll be an actual warranty claim is only 3%, so 0.03 here. All right, you can expand on this. So this is a multiplication rule for n independent events. So it could be 5, it could be 1,000, doesn't matter, okay? So if event 1, event 2, event 3, all the way to event n are independent events. So they're all independent. Okay, so meaning the occurrence of the first one does not impact the occurrence of the second one, and so on and so on. If I say, hey, what's the probability that E1 and E2 and E3 and all the way to En happen? You're just going to multiply all the individual events together. So you're just going to multiply the first probability of the first event times probability of the second event times all the way to the probability of the last event. So it's literally just expanding out the first rule we had. Now it's just, instead of just 2 events, there's 5, 10, 1,000 things happening. All right, so this one. Suppose you flip a coin 5 times in a row. What is the probability you get heads 5 times in a row? So probably head 5 times in a row. Well, you just have to figure out how to write this. The first needs to be a head. I'm just going to put first as H. And the second is an H, if I want them all to be heads in a row. And the third is an H. And the fourth flip. And the fifth one. So if I want 5 heads in a row, it makes sense that the first needs to be a head, and the second needs to be a head, and the third needs to be a head, and the fourth needs to be a head, and the fifth needs to be a head. So you see the and, that implies multiplication. So indeed, coin flips are all independent. So it's probably the first is head times the probability the second is a head times the probability the third is a head times probability the fourth is a head times the probability the fifth is a head. Well, what's the probability that you flip heads? It's just 1/2 times 1/2 times 1/2 times 1/2 times 1/2. Well, this is just 1/2 to the 5th power, which is 1 to the 5th power divided by 2 to the 5th power, which is 1 over 32, right? Because 2 times 2 is 4, 8, 16, 32. So pretty low odds that you'll flip a coin 5 times in a row and get heads 5 times in a row. All right, let's try this one. The probability that a randomly selected female we saw age 60 years old will survive the year is 99.186. Okay, so what is the probability that 4, we did 2 before, so what is the probability that 4 now survive the year? Well, so I want to find the probability all 4 survive. Well, just using the same with the coin flip, it's the first survives, and the second survives, and the third survives, and the fourth survives, right? Because if I want all 4 to survive, they all need to survive. Well, we know that it's independent, so it's just probably the first survives times probably the second survives, and so on and so on and so on, which is just 0.99186 times itself raised to the 4th power. And when you do that, you get 0.9678. So when I ask questions like, what's the probability they all survive or all of this happens, just write it, the first happens, and the second happens, and the third happens, and the fourth happens, so on and so on. All right, let's do now compute at least probabilities here. So the probability that a randomly selected female age 60 years old will survive the year is 0.99186. We got that. So what is the probability that at least one of 500 randomly selected 60-year-old females will die during the course of the year? Okay, so I'm going to select 500, okay? And I want to figure out what is the probability at least one dies. So here's the thing, whenever we do these at least one, you're going to use the complement rule. You can see it right here. All right, so what is the complement of at least one dies? Complement of at least one is none. Always, always, always. So the probability that at least one dies is 1 minus the probability that none die. Well, what that is the same thing. If none die, they all survive. So how did I get this next? The probability that all survive is 0.99186 to the 500th power. Well, this is 1 minus probably the first survives. And the second survives. And you would keep going all the way to the 500th survives. Well, the and statement would imply multiplication. So it would just be this multiplied by itself 500 times. So we're just raising it to the 500th power. And if you plug this into your calculator, you'll get the probability. And let me show you this, so you can see it here. And let me load up. Sorry, I should have loaded up my calculator beforehand. So if you take 1 minus 0.99186 raised to the 500th power, yeah, it's 0.9832. So it's almost a 100% chance that one of those 500 females will die in that year. All right, let's just do another one here. Another at least, okay? I find this problem really interesting. So this is about the Challenger disaster that occurred on January 28th, 1986. So if you don't know anything about the Challenger space shuttle disaster, you should read up on it. But basically it was the space shuttle Challenger shot into space. And on its way out into space, it exploded. Okay, and it was a big issue at the time. So what happened was, I'll skip ahead a little here. An exterior fuel tank failed because the seal around the tank failed. And what happened is the liquid nitrogen just caught fire and the ship just exploded. Okay, so let me give you some information. So every item on the space shuttle is given what's called a criticality rating. So every single piece that goes on the space shuttle, down to every single screw. So they classify the criticality as criticality 1, criticality 2, criticality 3, so on and so on. Criticality 1 items are items that act independently of each other. They have no backup. So let me give you, and they must also have a 99.99% reliability. So what that means is they work. The probability that the item works is 0.9999, really high. So let me give you an example of a criticality 1 item. The wings on the plane are classified as criticality 1. Right, like there's no backup wings, and the wings work independently of other systems. So on the Challenger space shuttle, there were 748 what they called criticality 1 items, okay? The other thing that's really important about criticality 1 items is that if a criticality 1 item fails, the space shuttle's a loss. Like, for example, if the wings fall off the plane, the shuttle's a loss. It's not going to make its way home. Okay, so for the Challenger shuttle, a criticality 1 item did fail. That exterior fuel tank failed because the seal around the tank failed. So let's compute a probability that was probably given to the astronauts before they took off. So let's compute the probability of a shuttle loss even prior to taking off. Okay, so what is the probability of a shuttle loss here? All right, so for this to happen, at least one of the criticality 1 items must fail. At least one of them fails. Okay, because remember I said if a criticality 1 item fails, the shuttle is a loss. Okay, so compute the probability at least one criticality 1 item fails. Well, at least one, so you're going to do the complement. The opposite of the complement of at least one is that none fail. So it's the probability, 1 minus the probability that all 748 items work. Well, we know the probability the first one works is 0.99999. Well, going back real quickly, it said they must act independently of each other. So I told you they're independent. So it's the first works, and the second works, and the third works, and all the way to the 748th works. So it would just be 0.9999 times itself 748 times. Well, if you plug this into your calculator, 1 minus 0.9999 raised to the 748th power, the probability that even before takeoff the shuttle wasn't going to make it home is over a 7% chance. It's 0.072 probability, okay, or a 7.2% chance that the shuttle wouldn't make it home even before it went into space. So those people were incredibly brave. I wouldn't get on a shuttle if they said, hey, there's a 7% chance it wouldn't make it. All right, class, I hope you found these examples interesting. And you'll have some of these questions asked in the class. And the big highlight here, just remember these at least probabilities to use the complement rule.